Hello, everyone. This is Steve Clark, the Deputy Associate Administrator for the Aeronautics Research Mission Directorate, and I am very excited about moderating this panel, Aeronautics in Space. With my background in both space and aeronautics, the two worlds actually do overlap, which a lot of people don't realize. A lot of work that is done in the aeronautics world directly applies to space exploration. And we're going to hear about that with some of the panelists. And if you think about it, kind of the mantra that we say here in aeronautics is that to get to space, you have to travel through the air, through the atmosphere. So that's aeronautics. And in a lot of cases, you bring either people or supplies or samples back. So you actually come back through the atmosphere twice. So a lot of the research we do in aeronautics directly applies to space exploration. And we're doing a lot of work with our Science Mission Directorate and our Space Technology Mission Directorate to bring together the strengths of all of NASA and particularly aeronautics to help with space exploration efforts. And so I'd like to tee up our panelists that we have today. First, we're going to have a short video on the Dragonfly project. This is a fantastic project where we're actually going to be flying a rotorcraft vehicle on another planetary body. You've heard about the Ingenuity, the Mars helicopter. Well, now we're going to be flying a larger craft on Titan. And I don't want to steal any thunder of our first panelist, but first let's go to the video and watch a short video by the Johns Hopkins University Applied Physics Lab.
Mission Go Command, ready? Mission Go Command, 3, 2, 1, go. I haven't landed. Landing.
Oh my gosh, that is so cool. I just cannot wait for this mission to actually launch and do its thing. So with that, I am going to introduce Ralph Lorenz, who is the mission architect for the Dragonfly mission, and he'll tell us a little bit more about it. So Ralph, take it away.
Yeah, thank you, Steve. So what you just saw on the video was basically a half-scale test platform. Titan is Saturn's largest moon. It's the only moon in the solar system with a thick atmosphere. and it has a gravity about the same as our own moon. So it's an environment that's uniquely favorable to heavier than air flight. And we are exploiting that much in the way the Mars rovers drive around to access different sites of scientific interest. We can travel much further by flying on Titan. And so Dragonfly is an octocopter vehicle. My job as mission architect is to specify the environment that this vehicle has to operate in, figure out what the winds and turbulence that it'll have to fly in are like. It drills to get samples from the surface, so I have to specify what kind of material we might drill into, how hard it is. And one point about Titan is that being so far from the sun, 10 astronomical units, it's very cold, 94 Kelvin or minus 180 Celsius. And that means we have to, we're operating in different aerodynamic environment from that of Earth. The Reynolds numbers are actually fairly high, which is very favorable for flight. We use some NASA wind tunnel facilities that can use heavier gases than air to match the conditions on Titan. But we also have to worry about these very low temperatures and their effects on materials. Choose metals that aren't brittle. There are flexible elements we have to pay attention to, and so material selection and testing is very important.
Okay, thank you, Ralph. I definitely appreciate that. And real quick question: how long is it going to take to get to Titan before we actually get to fly?
Unfortunately, outer solar system exploration is not a business for those seeking instant gratification. It takes us 6.5 years to get to Titan, so we plan to launch in 2027 and will arrive by 2034.
Awesome. We'll put that on our calendars, right? Well, and Ralph, you mentioned about the materials and really the tough requirements to select the right materials. This is where we can talk to Christine, and she can tell us a little bit more about materials and structures. So, Christine?
Sure. So my name is Christine Gregg. I spend a lot of time thinking about materials and structures, how we can manufacture them in new ways and make them stronger and stiffer for not just aeronautical applications, but for space. I was part of the MADCAT project, which is the Mission Adaptive Digital Composite Aerostructures Technology Project, which is a mouthful. But this is a picture of the wing that we built and tested in the wind tunnel over at Langley. And this is very big. It's like, I think 11 feet tip to tip. And it's filled with, I have a picture here of the gossamer lattice structure. And so our research project was trying to figure out ultralight materials, how we can change how we make structures to be more efficient for flying and manufacturing. But what was interesting is that now we've moved this technology over into the space world. So we're looking at how we can use this same manufacturing technology to help us make really large things in space with the help of robotics.
Wow, fantastic. So we might be able to see an airplane, or let's call it a plane, an aircraft of a larger scale on another planet someday, potentially, huh?
Absolutely. I know that there's been a few proposals for how we can not just fly with rotorcraft on other planets, or on other planetary bodies, but also perhaps with fixed wing one day.
Oh man, that's fantastic. Yep. So speaking of aircraft, and I think I mentioned in the beginning here that on the way to space, you have to go through the atmosphere, and that requires ground support equipment, right, and facilities to be able to support both space launch and aircraft. And that's where I'm going to switch over to Michael here for a few minutes, and maybe Michael, you can kind of tell us about transformation of spaceports and dual use, and handling all that traffic that's going up and down and around. So, Michael.
Yeah, no, I appreciate it, and thank you for having me. And really quite interesting. And then the area that I'm in is not as sexy as MADCAP or Dragonfly or some of the other space systems. We're kind of the Rodney Dangerfield of the industry, so to speak, in terms of not getting the respect, if you will, more or less. But our focus and my background has been recently focusing and supporting both NARI, the Aeronautics Research Institute, and also NASA headquarters, lunar architecture, and trying to ensure what we call operational support, operational availability of multiple dynamic systems in multiple deep regions of space beyond low Earth orbit. And how do we do that is we try to influence the early design phase of the life cycle to design for sustainment. Things like driving in not just component commonality, possibly material commonality, whereas we get into things like additive or regolith-based additive manufacturing or in space 3D printing, raw material feedstock is going to be critical. So we're looking at things like how can we identify and map out the potential parts for cannibalization or substitution if we have a need or failure, as it were, as well as other mechanisms to reduce the logistics footprint, if you will, the need for Earth-based sourcing materials. So we're living truly in situ, per se, in terms of living off the land, as it were, making Earth irrelevant in a sense for material support. So again, we're not as the sexy field, as it were, but most important to understand that it's really about ensuring that operation success or mission success, as it were, and ensuring that there's on-time demand, support, and needs fulfilled in terms of mission requirements. So yeah, our job, of course, is to work very closely with design engineering and making sure that the long-term support is not just supportable per se, but also affordable. So we're looking at all what we call the ilities: reliability, maintainability, supportability, and of course affordability. That's all throughout the whole life cycle of any system design.
Yeah, Michael, and I think you make a point, at least that I took away from that, is we do this early research with various spacecraft and even in aircraft here on Earth first, but you got to have that logistics supply chain to kind of build up the infrastructure. Once you've done the reconnaissance, I almost used the word recon, but didn't want to go short there. Then if you want a more sustained exploration path, right, you got to set up that logistic supply chain to make it sustainable. And that's a lot of what kind of research you've been involved with and continue to be in helps, right?
Yeah, no, we're looking, and we've developed a very unique hybrid geographic modeling capability of what we call campaign level distribution modeling for support to lunar surface locations, to cislunar. We're also looking at supply chain economic resiliency of sourcing, as well as the adoption rate of sourcing through 3D printing, and what kind of effect does that have on traditional supply base that were required, let's say, through CNC process. So we are, it's interesting, supply chain risk, distribution disruption is in vogue now. We've been doing this for, in terms of the modeling capabilities that we have, almost 20 years. And it's interesting to see now the issue of ensuring a very extended supply chain is being addressed, which we're thrilled about, because that was always our concerns. That let's put it this way: there's an old saying, for want of a nail, a kingdom was lost. So it's very critical that we're able to support these systems.
Yeah, yep, very true. Well, thank you all for kind of giving us a little overview here of your various expertise. And how about we go back over here to the questions? We've got a couple in the queue. And I'm going to open this up to everyone. Very interesting question, too, is have you considered using the railgun for a low Earth orbit launch propulsion system? And their idea is run the railgun right up the side of Mount Kilimanjaro and launch away. So who would like to take a shot at that?
Well, that's an old idea. I think it's talked about in science fiction from the 70s. It's an attractive prospect to give a vehicle much of the energy it needs to get to orbit on a surface infrastructure asset, a big long linear accelerator, because that then takes the whole rocket equation and large amounts of propellant out of the story. It makes it in some senses a much more sustainable effort, because the energy source could be renewables, could be nuclear, whatever. The big challenge has always been that such a large infrastructure element is a major investment, and that sort of big upfront cost is always a big bite to take politically. And then you have the issue that you are suddenly going at near orbital speeds in the near surface atmosphere, which introduces lots of aerodynamic heating challenges. So you can't have a spidery little satellite with antennas and solar panels screaming through the air at 7 kilometers a second near the surface. So you need to encapsulate it in some sort of thermal protection, and you've got hypersonic stability considerations to worry about. So is there a place for it? Maybe. I mean, my suspicion is that sort of system might be most useful on the moon to send resources elsewhere. Sometime in the future, when we have a pan solar system economy, getting out of the Earth's gravity well and getting through its atmosphere, giving all the energy at the beginning, may not be the answer for many systems.
Yeah, that's really good points made, Ralph. And you touched on the aerodynamic heating. So, Christine, have you all looked at that challenge of having all of that initial energy at the beginning and going up through the atmosphere?
I'm sure someone has. I can't claim that I have. But there's a large thermal protection group here at NASA Ames that develops all of the new thermal protection that we need to go to Mars, or that we need to actually go to the moon or Mars and bring something back. And I know that it's often said the challenge of going to Mars is that you have not enough atmosphere that it helps you slow down, but enough atmosphere that it'll blow you up if you don't pay attention to it. So, it cannot be overstated how much aerodynamics and the material science needs to be addressed and can't be ignored for not only launching here from Earth, or just getting to where we need to go on other planetary bodies that have an atmosphere.
Yeah, good point. And I know we do a lot of entry, descent, and landing research from a material standpoint with our space colleagues. And like you said, the Mars in particular, we're looking at one day hopefully launching much larger structures to enter the Mars atmosphere, much larger than what we're doing today with the rovers, such as landing craft with humans. Right. And so we've got to solve that scalability issue with materials on how do you do that. So again, lots of work across the agency to solve those challenges. Right.
It's
a
huge challenge.
Oh, go ahead. I'm sorry.
Oh, no, I just wanted to say it was a huge challenge. And I also think that inherent in those development of those systems, and also thinking about, well, how do we reduce the amount of stuff that we need to take? I think it comes down a lot to manufacturing. And, luckily there's a lot going on, not only in aeronautics research, about how do we manufacture more complex things with composite materials? How do we do more complex things with 3D printing that hopefully we'll be able to leverage, that could be very much game changers and enabling technologies for getting larger things to the surface of Mars.
Absolutely.
Very well said. And Michael, I was thinking, and you can certainly answer and add to anything that Christine and Ralph just said, but I was just thinking kind of from a spaceport standpoint, the person who asked the question mentioned Mount Kilimanjaro, and I understand why, but are there other potential ways that commercial companies could launch spacecraft, say, from a spaceport such as the Kennedy Space Center using like the shuttle landing facility, which is a 3-mile long runway. Very flat, of course, there in Florida, but are there other concepts being considered?
There are, and in fact, we've partnered with Space Florida, which is a organization here in the state of Florida that operates and manages currently the old former SLF, the shuttle landing facility. There's also activity going on at the Space Coast Airport, which is in Titusville, Florida. That is familiar with the area, the geographic region. It's on the other side of the Indian River, very close to Kennedy Space Center. And so, yeah, there's a multitude of efforts that are underway currently here at Kennedy Space Center, as well as other centers too. We have a lot of activity at Wallops as an example, and so that's exciting for us because it proves out viability, if you will, of demand in the sense, or the economics of commercial space, meaning there's a demand for it. So good. I'll revert back to logistics. That's a good thing for us because that means that material sourcing is not going to be as difficult because there is that demand. There's profitability in materials and technologies. So it's kind of becoming what we would call a cluster, a manufacturing industrial-based cluster here in Florida is beautiful. You'll have different and complementing technologies, manufacturers. So it's a very good from a supply chain and manufacturing perspective. You're going to see a lot of improvement in terms of availability, product quality, and reduced time to develop certain things. So in short, yeah, we're definitely seeing a lot of activities here in this region. And time will tell who wins and dominates on the economics of it.
Yeah, I wonder if I can pick up on that point and something Christine said. In the planetary aeronautics field, such as it is, we saw a couple of helium balloons that the Soviet Union sent to Venus back in '84. We've got the Ingenuity helicopter operating on Mars right now, and Dragonfly in development. And maybe there's some, fixed wing ideas as well kicking around. But, each different environment seems to have a different right answer. And it, in a way, kind of harkens back to a century before in terrestrial aeronautics. You look at the 1920s, nobody knew what the right answer for flying was, right? Are we going to cross the ocean in Zeppelins? Or are we going to, be using fixed wing? Or what's the right answer? And of course, we have different missions for these kind of platforms, and the introduction of new manufacturing techniques like additive manufacturing and the possibilities for structural composites, as well as what is also new, the sort of opportunity for distributed power with new electrical systems, electric motors and rotors, has opened up this sort of new space in urban air mobility, the flying taxi kind of arena. And there's just this, Cambrian explosion, this proliferation of vehicle types. Some are octocopters, quadcopters, some are, tilt rotors, some are blown flap wings. There's just every configuration you can imagine being explored right now, which is, tremendously exciting from a technical standpoint. Of course, economically, we'll see the harsh reality of economics and operating costs and maintenance and all that swinging into cull the less fit design alternatives. But it's an amazing time to be involved in aeronautics right now.
If I may, to add to Ralph's comment, is that it's also an importance of system engineering, system integration. So you have these multiple systems, multiple technologies, and it's going to get complicated fast. So we're going to have some type of mechanism or means, if you will, to be able to work collectively. It's almost anyway, yeah. So some way to integrate systems together.
Very true. Very true. Go ahead, Christine, and then we'll jump to the next question.
Sure. Yeah, Ralph, and I was just thinking, you said there was such an explosion of technology just here on Earth, and we have, this is one example of an atmosphere and an environment. And, we think about space applications where if you're going to Titan or going to Mars or going to be on Venus, those are so different. And so, I think if you add in other planetary bodies, the amount of solutions that all of a sudden could make sense really change. And I think also, just going back to manufacturing, you have to also think about, what getting something through Earth's atmosphere, that's a different structure than what wants to exist in 0G in space, than perhaps wants to exist on, whatever planetary body you're visiting. So thinking about doing in-space manufacturing, in-space assembly really becomes important for, I think, the viability of a lot of these technologies.
Yeah, Christine, that's an excellent point. So we got to look at it, from different angles, right? To look for the right solutions for the right case to solve those design challenges, and that's a really good point. You don't always have to start with 1G on the surface of the planet, right? So, well, let me jump to the questions, because one of the more popular ones, somebody wrote that they had an opportunity to work with some small businesses to develop some unmanned aerial vehicles, UAVs, for Venus and Titan under the NASA Small Business Innovative Research Program. And they also had the opportunity to develop a Venus mission concept with Venus scientists and technology experts. And they were surprised how little was known about NASA UAV research. So the question is, how do we better spread the word, especially for missions in the distant future?
Not sure how to hit that. So one I think important point to recognize, sort of historically, is that early aircraft development was completely tied to the pilot, right? The functions of guidance and control and managing the whole operation, loading the passengers, avoiding other traffic, was all executed by a pilot. Whereas the technology area that really gets pushed in space exploration and planetary exploration in particular, where the distances mean the one-way light time for any kind of control interaction is minutes or hours. So that forces you to have a lot of autonomy, and I think the capabilities for safe autonomous operation that in some respects are pioneered in spacecraft are coming back to Earth a little bit in systems like unmanned aerial vehicles. Now, of course, there are opportunities for UAVs or drone or whatever at other planetary bodies, and it's very much up to the customer, if you like, the mission, the people that formulate the missions, the planetary scientists and so on, to seek out the technologies that enable the missions, and how to do that, especially in a commercial environment where there may be technologies that are considered proprietary, right? You really need sort of an enterprising individual to kind of sniff out those technologies that are out there that might give them a competitive edge in a mission proposal.
Mm-hmm. Yeah, thanks for those insights. Yeah, that's I think maybe I can jump in a little bit on that too. Is we are working closely together across the mission directorates within NASA, and we're looking at new mission concepts and how Aero can help, particularly with those planetary bodies that have atmospheres, and there are considerations of flying some type of craft to do the science research. But certainly, people like Ralph and others who have experience working with NASA across those mission directorates can also talk to the various mission designers, science community. I expect there will be, particularly after Dragonfly, there is going to be a ton of papers written. on the science data that's actually acquired and analyzed, and the fact that how it was acquired, right? With a rotorcraft.
Dragonfly, was proposed to NASA in 2017, right? That's already 6 years ago, and it's got a long way ahead of it. But I remember advocating that rotorcraft might be a good way for Titan back in 2000, and 2002, 2003. I went to some unmanned aerial vehicle conferences, and I can assure you I was the only planetary scientist there, right? But you need to bridge that gap between technology, engineering, and science to spot those opportunities. The Ingenuity helicopter, came about in a rather different way. It was more of a sort of technological opportunity, right? Ingenuity was designed just to show that rotorcraft flight was possible on Mars, where it's the thin atmosphere makes it very, very difficult. And it kind of got added on to an existing science mission, the Perseverance rover. Dragonfly kind of is enabled by the technology and is itself the size of the Perseverance rover. So they're completely different, and actually you can learn more about them in a recent book I have published by the AIAA. But how in NASA do you bridge the directorates, right? I mean, they're literally stovepiped. So how do you get the technologists and the scientists to talk to each other?
And we are working on doing just that, Ralph. So we've been looking at potentially workshops across the mission directorates and doing some brainstorming on that. So I think we're going to see some additional progress coming out of those types of things, right?
I think it's hugely important. Yeah, there was actually a planetary technology workshop in Texas last month that the STMD, I think, was very vigorous in promoting, and it was a very productive interchange, right? It's those sort of cross-disciplinary interactions that a lot of the innovation is going to come from.
I also just want to say that, it does take a lot of advocacy and a lot of sticking with it and time, because I think NASA has a lot of good ideas. They're in the position of having many good things to do, and so it really takes perseverance, even for good ideas, just to get them through the process.
If I can add to that, we've got the commercialization effort. There's a lot of NASA technologies that are in the book, so to speak, and on the shelf to be commercialized. But you have to have almost your secret decoder and understand exactly what you're looking at in those reports and in the technologies. I think that's one thing where NASA as an agency could maybe do a better of in terms of the marketing or pushing some of those technologies that are ready to go in terms of TRL levels or technology readiness for prime time. So maybe it's as simple as a outreach effort. I'm not sure, but it's a good question. At the end of the day, public support needs to be involved and engaged and fully with us for us to really flourish.
Yep, completely agree. Appreciate everybody's comments on that. That's excellent. Here's another popular one. It had more than one vote on this. What are some of the experimental test challenges when it comes to mimicking microgravity conditions?
The fact that we live on a planet with gravity, yeah. So I mean, there are some exciting, commercial opportunities there now too, right? There are commercial operators of G flights, right?
Right.
Aircraft that do parabolas, and we're seeing, as the sort of commercial space sector, develops large launch vehicles. Some of those have, suborbital capabilities initially that can offer some microgravity, for a period that's longer than you can achieve in a parabolic flight or a drop tube. but for sure, yeah, that's one of the big things difficult to do.
Ralph, I have a question for you in that regard. We can emulate to some degree the mechanical properties, but how about the chemical properties of the atmospheres and some of these interplanetary surfaces?
Yeah, that's an interesting question of just how faithful you have to be. In aeronautics, we're used to matching the Reynolds number and Mach number, and that's all you need to do. But there are some other subtleties, like example, Dragonfly uses a laser laser system, a LiDAR, to detect obstacles on the surface. And a lot of automotive LiDARs use diode lasers that are at a particular wavelength, that the few percent of methane in Titan's atmosphere, which aeronautically insignificant, that small amount of gas absorbs light at just the wrong wavelength for those lasers to work. So you have to use particular types of laser that fit the atmospheric properties. So it's kind of a case-by-case thing. Venus is challenging because you've got sulfuric acid clouds. That's a real materials challenge for things like parachutes and so on. So yeah, there's not an overall answer. You just have to think through exactly what the interactions are going to be with the environment, which is what I do for a living, which is kind of fun, right? You just have to transport your mind to this alien environment and guess what's going to happen, and make sure you select the materials and processes and systems accordingly.
And also, going back to the mimicking microgravity, within the Space Technology Mission Directorate, there's a program called Flight Opportunities. And I know they have relationships with Blue Origin on their New Shepard. A number of experiments have been launched on that suborbital launch vehicle and recovered. And, that mimics microgravity somewhat for a short amount of time. And then, of course, sending experiments up to the International Space Station and doing testing up there, and then bringing them back for analysis. That's always an opportunity as well. And, we're hearing about commercial companies developing commercial space platforms in low Earth orbit. So I think there's going to be even more opportunity to test out technologies and so forth in microgravity, let alone the test facilities that we here have on the ground in, environmental test chambers and so forth like that. So I think there'll be opportunities to do that. Let's see. Another question. What other planetary bodies would you want to see air vehicles operating on? Are there any you wouldn't want to design vehicles for?
So that's a good question.
Yeah, that's good.
Well, let me kick off. I mean, Dragonfly is going to Titan, which is the easiest place to fly in, right? So do you want to go to fly in another planetary body because it's particularly challenging, or because there's a scientific question that flying helps you answer? There are fascinating dynamics and chemistry and cloud tops of Jupiter, for example. That's not a particularly easy place to get to, nor is it a particularly easy place to fly in, but it'd be spectacular. Yeah, I mean, take your pick.
I've always been partial to the Venus airships. There's just something about it. I think there's so much interesting science to be done on Venus, and steampunk Venus airships. Like, who's going to say no to that? That's great.
But it's funny you should mention that. There's actually a NASA Discovery mission under development now called Da Vinci, which is a probe, right? It's just going to fall under a parachute initially and then free fall. But the Venus atmosphere near the surface, it's hellishly hot, so you need to make the thing like a pressure vessel, and it's insulated, but it's so dense that to make an accurate descent time prediction, you actually have to factor in the buoyancy of of this body immersed in a fluid, right? The density is what, 1/16 of water. It's enough to make a difference. So in a way, it's like an airship, right? But for sure, airships are wonderful machines. In a way, they're like submarines of the air. I had an opportunity to fly in a pedal-powered airship once, and it was just a magical experience.
Wow, I'll bet that was. Well, and Christine, from a material standpoint, you mentioned Venus is your favorite, and I know there is what I've seen a renewed focus on exploring Venus. From a material standpoint, though, what kind of challenges do you see? Supporting space exploration from a materials aspect.
I mean, the sulfuric acid clouds, that's definitely a challenge. But I think it's solvable. And I think in terms of, looking at the material requirements, if you can figure out how to get yourself, about 50 kilometers above the surface, you actually, Earth's atmosphere is buoyant there. So you can actually do quite a bit with the materials that we have if you can solve the chemistry problem sort of to shield yourself from the outside. It actually seems tantalizingly doable. So I'd love to see sort of more studies looking at how that could actually work, solving the chemistry problem and solving the sort of insertion problem, because I think the other parts of it are actually, from a structure standpoint, not too bad.
So I got to ask that flip side question, are there any planetary bodies that, it just would be too hard? And even if the science research is compelling, do we want to stay away from?
Triton and Pluto have atmospheres, they have hazes and surface features that are influenced by the atmosphere, but the air is really, really so thin that aeronautics just isn't practical.
There you go.
Yeah, Mars. I've been impressed with how well the Mars helicopter has done. So I think Mars is something like a practical limit in terms of the immensity.
Yeah, that makes sense. And there's another question related to that was a good segue into Mars ingenuity. I'm not sure if anyone really has some insight into this, but they said, we watched Mars ingenuity helicopter land. It was so cool. Weren't there a lot of off-the-shelf technologies used?
You can read all about them in the book that's not showing here. Yes, there were. I mean, the Ingenuity vehicle was very small, 1.8 kilograms, and the degree of miniaturization, that modern cell phone technologies and so on, the sensors and the processing capability, really is enabling for that. Because it was a technology demonstration, they're sort of allowed to use a wider range of parts than is traditional. It's kind of a perversity that as an organization is quite technologically conservative, right? Fly things in space, if you really know they work, which comes down to, did they fly in space before? So there's a sort of activation barrier in getting new technologies into space, and these kind of technology demonstration opportunities are important for that.
If I may inject that, one of the things concerns was also microelectronics, taking a commercial off-the-shelf plastic packaging, and in the shake and bake environment of the extreme space environment, let's say, it was a question. It used to be where we had to have rad-hardened microelectronics. That still is a concern. But that, in terms of off the shelf, that is one area to really need to be focused on also as we move forward with off the shelf items. Can it handle the shake and bake environment, let's call it, of deep space?
There's also a big difference, I think, in requirements for components based on how mission critical they are. So I think it is important to remember that Ingenuity was a technology demonstration. And
exactly.
While everyone's super invested in it, it's a little bit different than if it is the entire mission, and you've really got to make sure that it succeeds, especially for something like a human spaceflight or something like that. There are vastly different requirements for that and the risks that people are able to accept.
Crit features, or crit 1, 2, and 3, as we would call it, critical in terms of life, mission, or vehicle, also would be defined as we move out in terms of reliability.
And good points by all of you. And I can just kind of reflect on some knowledge. You're right, Christine. The Mars Ingenuity helicopter was a secondary payload, as they called it. If it didn't work, it did not affect the primary mission, which was the rover. And so it could do no harm. It couldn't be late delivery to be integrated. And so it made it. And I think it has really changed the paradigm of scientific research, though, on Mars and potentially other planetary bodies as well. So I expect there'll be a lot more work to do across the NASA mission directorates working together to solve these problems. And I certainly look forward to seeing the accomplishments that'll come out of that additional work. So I got to tell you, this has been a fascinating panel, and I really do appreciate all of your time. Excuse me. I think we are just about out of time, and we did manage to answer all of the questions that people had in I/O. Angela, turn it over to you.
Thank you, Steve. Thank you to all the amazing panel, giving us, the audience, a great perception of how technologies are being developed in aeronautics, but then they're also being contributing to space missions. So thank you all for being with us today. And then John and I are going to close out the past 3 days here shortly.